Hey, we had the Schwarzschild Metric, and I'm Audrey.
I'm Kylie.
And I'm Raquel.
And the Schwarzschild Metric is basically just a solution to Einstein's field equations of general relativity that talks about a gravitational field around a spherical mass.
Okay, so this is our Schwarzschild metric, and then here you can see that C right here is going to be the speed of light, tau is proper time, and then we have an R with the subscript S, and that's the Schwarzschild radius, and that's measured by 2gm over c squared, and g is the gravitational constant, where m is the mass in that. And then, just like we did in class, we have the Schwarzschild metric with t as time, and then we have r over there is the radial coordinate, and then we have theta and tau as well in that. And then Audrey is going to talk about geodesics.
Okay, so for our geometric connection to differential geometry, we're going to talk about geodesics, and in particular, I'm going to specify on geodesic orbits because those just made the most sense. Here are the four main geodesic equations, and they look like a lot, but because we're doing geodesic orbits where we have spherical symmetry and orbits stay in a plane, so you can choose initial conditions of theta equals pi over 2. That might be hard to see, but and that, and you can see if you choose these, even this really long geodesic equation just simplifies because of all these thetas and u's, and it makes it a lot simpler. But anyways, you end up getting this function that states conservation of angular momentum, and it's similar if not the same to the radial geodesics, so that helps a lot. And there's also null geodesics, which I'm not really going to get into, but if you consider the null case of this, you get null geodesics. Okay, this is Karl Schwarzschild. He was a German physicist and astronomer. He found the exact solution to the Schwarzschild solution, which is our metric. He did this in 1915 and published it in 1916, and it was the first exact solution to Einstein's field equations.
One article I found interesting was an isoperimetric comparison theorem for Schwarzschild space and other manifolds. It was published by American Mathematical Society and was written by Hubert Bray and Frank Morgan. The article talks about how geometrically the Schwarzschild metric is spherically symmetric and has zero scalar curvature. Physically, this metric corresponds to a totally geodesic space-like slice of the usual 3D Schwarzschild space, which is a spherically symmetric black hole in vacuum. In Schwarzschild metric, every sphere of revolution is uniquely minimizing. One interesting feature of the Schwarzschild metric is the Schwarzschild black hole, which is a black hole that does not have electric charge or angular momentum. It can only be distinguished by its mass. It is characterized by a surrounding spherical boundary called an event horizon, which is situated at the Schwarzschild radius.
Okay, here you can see that radius in the red, and that is what I mentioned earlier on the whiteboard with the Schwarzschild radius, and pretty much your eye cannot see past this point. It's going to be a complete black hole. And then a real-life example of that is going to be on your left is the Schwarzschild, and then on your right is the Kerr metric, and you can see kind of the Kerr has more of the funnel shape, whereas the Schwarzschild is more of a drop-off. For an example, you could see like the radius here, and if you were a boat and traveling along the Schwarzschild radius, if you went in any amount, you would get sucked into the black hole in this. And you can find all of our references in the description bar below.